Alright, welcome back. So this is still part 2 of our basic chemistry, and this is the time we're going to look at the second type of bonding, which is called covalent bonding. Now we've looked at ionic bonding. We understand the structure of an atom. We understand that the electrons on the outside in the groups 1 to 7 elements are not full, and therefore they have to interact with other atoms in order to try and make a full outer shell. Now in ionic bonding, that's where a small, a group 1, 2 and sometimes 3 element donates electrons to a group 7, usually chloride. Fluoride could be another one, but chloride's the most common biologically. So that forms a simple magnetic attraction. You lose one electron, or 2 or 3 depending on which group, and the chloride takes 1 electron regardless. So if it's a group 3 and it's giving 3 electrons away, you're going to need 3 chlorides to take that, so it would be AlCl, so aluminum as you say here, but aluminium 1, chloride 3, for example. Alright, so now we're going to look at the covalent. Now, the valence shell is the shell which is on the outside of the given atom, depending how many electrons that atom has. So the valence shell for hydrogen is this one, because it only has 1 electron. The valence shell for lithium is this one, because it has 2 here and then 1 here. The valence shell for sodium is this one, because it's got 2 here, 8 here, and 1 here. The valence shell for potassium is this one, because it's got 2, 8, 8, and 1. So the valence shell means the outer shell. Now think of your skin. You can see your skin, you can look at your skin, but you're not looking at all of your skin. You're looking at the valence layer of your skin. You're looking at the outer layer of your skin. You have multiple layers sitting underneath the outer layer, which then help protect the inner structures from all the bacteria and everything else outside, and even just simple water loss. So the skin isn't like 1 layer thick, it's multiple layers thick. So think of the outer layer as your valence layer, and that will help to make some sense of what's coming next. So we've actually given the name of the type of bond already, so let's write it out. So in this particular bonding, it's going to be, I'll do black because I'll merge with the other ones, do it in red. Let's do actually let's do it in 2 colours. Let's get really crazy. Covalent bonding. So, co is short for cooperate, so to share. So co means to share. Now, valent is a version of this word here, valence shell, and it refers to the outer shell of the atoms involved. So share So covalent means to share the outer electron shell with another element that also requires to do so. So this is different from ionic bonding because you're not donating the electron and you're not receiving a whole electron. You're sharing existing ones together. So there are 2 types of covalent, or sharing of these outer electrons. The first type is non-polar. And then the second type is simply polar. Bonds. So now we know that a covalent bond is the sharing of the outer electron shell between the 2 involved atoms. They can share them in a non-polar fashion or a polar fashion. Now, what does that mean? Well, polar, remember the North Pole and the South Pole? They're poles apart. They're as far apart as you can get. Polar means that one side holds a different charge to the other side. Whereas non-polar means there's no overall charge. So again, we're talking about charge, and that is going to become an important theme all the way through physiology. Is it charged or is it not charged? Because if it's charged, it's going to interact with other things that are charged, magnetic, etc. Whereas if it's not charged, it won't only not interact with things that are charged, it will shun them, it will move away from them. So, let's get some space and do some examples. So I'm not going to spend a lot of time on this, but I'm going to start with a non-polar example. Think of non-polar as no charge or free. Covalent bond. No charge, covalent, no charge while sharing outer electron shell. So non-polar covalent bonds really in English says no charge while sharing outer electron shell bond. You can kind of indicate or see why saying no charge while sharing outer electron shell doesn't really trip off the tongue very well. So non-polar covalent bond at least does sound a little bit more sensible in that change. So what is it? Well, let's look at carbon. Carbon is here. Carbon is in group 4, so that tells you there are 4 in its outer shell. So if we draw carbon, it's going to have, it's 6, it's actually 6, 12 normal carbon. So if we actually did it properly, we do 6 of them, 6 protons in the nucleus, then you'd have 6 neutrons, separating them out. So there's your nucleus. Now on the outside of that, you're going to have electrons. So first shell has 2, so that's full up. It's a 6 protons, so it's got 6 electrons. So the second shell can hold 8, but you only actually have 4. So you've got spaces for another 4 to give it a full outer shell. So this is carbon. Now, biologically, very commonly, carbon will associate with hydrogen, and hydrogen is 1 proton surrounded by 1 electron. So hydrogen needs 1 to become full in its outer shell. Carbon needs 4. So you're going to need more than 1 hydrogen to get this to work, but we'll just work with this hydrogen right now. So this hydrogen can come over here. I'm just going to turn this around a little bit. So this hydrogen can orientate itself this way, and the carbon can also orientate itself toward the hydrogen, and that means that they can share these electrons. Now, they share, they don't give. So this electron spends 50% of its time with the hydrogen, and it spends 50% of its time with the carbon. So when it's spending 50% of its time here, and this electron is doing exactly the same thing. So at certain points, this electron and this electron will be with the hydrogen, and the hydrogen will have a full outer shell for a brief moment, but it's stable. At other times, this electron and this electron will actually be part of the carbon, and the carbon is therefore more stable for that bond. But for the carbon to be fully stable, it needs to do the same thing with 3 other hydrogens. And so they can all share, and so at certain points carbon will have a full outer shell of 8 because it's borrowing the electrons from the hydrogens, and a moment later the hydrogens will have a full outer shell of 2. Now to draw that, write it by notation, you've got 1 carbon and you've got 1, 2, 3, 4 hydrogens. That, chemically, is methane, and methane is gas. But because carbon can create 4 possible bonds, it makes carbon incredibly useful biologically, because it can create lots of different structures. If you add another carbon on here, then you've got another 3 bonds here. Put another one here, you've got another 3 bonds here, etc. You can make almost any structure using carbon as the backbone. And that is why all living things, well, 95% of all living things we have found are based off carbon as its skeleton, as its molecular skeleton, because you can go off in any direction with it forming these non-polar covalent bonds. Now remind yourselves why it's non-polar. It is non-polar because there's an equal sharing of these electrons. 50% here, 50% here. This one, 50% here, 50% here. So at any given moment, the negative charge here and the negative charge here is balancing itself out with the positives of the protons of the hydrogen and of the carbon species involved. So non-polar means no overall charge, just in the same way as we described it with an atom. So non-polar covalent bonds result in molecules which don't carry any charge, and therefore they don't interact with things that do carry charge. Now, we'll find out in a little while that those things are called hydrophobic, or water-hating, or water-fearing. And the fats, and the lipids as the bigger group of fats, including the steroids, are a major biological set of molecules which are all non-polar covalently bonded, or the majority of them are, so therefore they don't interact with things that are. Now water, as we'll see in the next talk, carries a small amount of charge on it. Actually we can do that in this talk, may as well get it done. So we'll see that fats and water won't mix, and we can now explain why. So here is our non-polar covalent bond. Now, let's stick with hydrogen. Now, let's take away the non, which makes us take away the no. Alright, so let's redraw our hydrogen. Okay, so now we have removed the non-polar, so now I have polar covalent bonds, so we've taken away the non, we've taken away the no, now we've got charge while sharing out a shell electron. Polar, it has charge on it, meaning it will act like a magnet. Okay, so how does that work? Well, we're going to use hydrogen again. This time, instead of carbon at the centre, we're going to put in oxygen. Now, oxygen is here, and it's in group 6, so it has 6 on its outer membrane. So I'm just going to put in, nucleus this time, because I'm going to draw it all out. So the nucleus has protons and neutrons in it, and then around the outside we've got, let's do it in blue, it's fine. The first shell, 2, and then we've got 6 in the next one. So we've got 2 possibles for oxygen, and again hydrogen just needs the 1. So oxygen could form with 2 hydrogen molecules in order to get or share the electrons it needs to become stable. And again, of course, hydrogen just needs the 1 electron. So let's do that. Let's share this one, and then let's share one down here. And I'm probably going to adjust that one in a moment. So another hydrogen comes up and it shares. Its bond. Let's just do that. So there's oxygen now. This is hydrogen. This is hydrogen. Now remember, water's molecule is H2O. So there's a hydrogen, there's a hydrogen, there's your H2, and there's your O. Now I just got finished saying that the sharing of this and the sharing of this is polar. It creates a charge. And so how does that happen? Well, the oxygen, and particularly oxygen in living organisms, does not share electrons equally with other elements that it bonds with, except for itself, because it has the same amount of pull one side to the other. So consider the sharing of electrons a bit like a tug of war. Now with carbon and hydrogen, the tug of war is equal. You've got same strength on either side, so no one ever wins. It's just basically, held at the centre. It's much more dynamic than that, but the analogy works well enough. In the case of oxygen, oxygen is many, many times more powerful than most of the other electrons in terms of pulling the electron off the other element it's sharing electrons with. So in this case it's hydrogen. So instead of being 50-50, we have a change. The electron from the hydrogen spends much more of its time close to the oxygen because the oxygen just has a greater pull. It's called electronegativity, and it means that it can pull the electron off the hydrogen, but it doesn't pull it all the way. It just doesn't become an ionic bond by just yanking the whole electron off. Instead, it holds it here for, say, just greater than 50% of the time. So that could be 75, that could be 80, whichever, but most of the time the electron spends here and the electron from this hydrogen spends here. Now because it's carrying a negative charge with it, the oxygen takes on a partial negative charge. Now that little funny skewy thing I just there is called a delta. You can write it out as partial, and you can even just put it in brackets. All of these things mean that that's not one full charge, which would make it an ionic situation because you've got rid of the electron or received the electron completely. In a partial charge, it means that the electron does still spend some time around here, just not very often. So it spends more time over here. So it donates a little bit of its negative charge, and there's 2 of them because there's one on this side and one on this side, because the actual water molecule is structured at 120 degrees. What am I doing? Like that. So the oxygen ends up with a slightly overall negative charge because of the electrons sitting here and here from the hydrogens. And so the hydrogens end up with a partially positive charge. So they end up out here slightly positive because the electron spends more time away from it than is with it. But there are very small amounts of time when both electrons are still around the hydrogen, so it keeps it stable. So this becomes polar because the oxygen has a slightly negative charge and the hydrogens have a slightly positive or partially positive charge. And that's the difference between a non-polar and a polar covalent bond. They're both very, very strong because it's sharing, and neither one wants to give that up if it can possibly avoid it. So they're much stronger than ionic bonds. But they're different because of the pull of the oxygen. So when oxygen makes covalent bonds with other elements, except for itself, when it makes it with hydrogen or it makes it with carbon, etc., it creates a polar covalent bond. So when you see oxygen in molecules, you know that those bonds are going to be polar covalent bonds because of the pull of the oxygen species. So because it's magnet, a polar covalent bond will interact with ionic bonds because they carry charge as well. So water, which has the polar covalent bonds joining the oxygen to the hydrogens, will interact with sodium chloride that we looked at earlier because that's positive and negative. Sodium's positive, chloride's negative. So when you put sodium chloride into water, well, you've got the chloride associating with that positive charge there because they're negative, and then you've got the sodium attracted to the oxygen because it's positively charged and that's negatively charged. And that's why when you dump a teaspoonful of salt into water and stir it, you see the salt disappear because they're breaking up and interacting with the individual water molecules. So they're separating out, so they disappear to your eyes because you can't see that level of resolution. Alright, so we've talked about ionic bonding, we've talked about covalent, we understand what covalent means, sharing of the outer electron shell, and we now know that there's two ways of doing that. That there is a way where no charge overall is created, we call that a non-polar or no charge covalent bond, and that's between things like carbon and hydrogen, most other species, unless you see oxygen in it. And if oxygen's in there, then it will create what we call a polar covalent charge because the oxygen will pull the shared electrons from the other element closer to the oxygen, carrying that negative charge toward its center, leaving the element sharing, usually hydrogen for example, with a slightly positive charge. And so again, because they have charge, they interact magnetically. And that makes them water-loving because water is charged. It carries a slight charge on it. So water is called a universal solvent because anything with charge, because most things in our world carries a little bit of charge on it, will dissolve itself in water. Alright, well thank you for listening.